All right, so this is Chapter 7, Newton's third law. And this is really a continuation of Chapter 6. So we're doing forces and we're doing kinematics. So here are the objectives, only 4. To learn how two systems interact, to identify action-reaction pairs of forces, to understand and use Newton's third law, to understand how to use propulsion forces and tension forces. Now here's something that's important. Physics education research has repeatedly shown that Newton's third law is the most difficult topic conceptually in all of Newtonian physics. So, a lot of people can recite it, but they have no clue what it really means. So, why do I tell you that? Because you might want to spend some extra time understanding the concepts. Okay, so what's a force? A force is an interaction between two or more objects. So now in this chapter we're actually going to study the interactions. All right. Okay, so the first thing I want to do is I want to hit the cart. Okay, so how would the cart explain what just happened to it? Well, the cart would say, I'm sitting there minding my own business, and this hand all of a sudden comes and hits me. Okay. Now, how would the hand describe it? So what I want you to do is think about, put yourself in the reference frame of the hand and assume that the hand is stationary. I mean, we can do that. So what would the hand say? The hand would say, I'm standing there minding my own business, and all of a sudden this cart comes up and smacks me. I mean, right? Again, there's two reference frames, right? I mean, there's two ways of looking at it, from the perspective of the cart and the perspective of the hand. Now, here's the question. How many slaps are there? There's one, right? There's one slap. And so, wouldn't you say that the cart is going to say, that there was a certain amount of force in this direction, but what's the hand going to say? Same amount of force in that direction. So all I'm saying is there's only one slap, and the forces are the same, right? The force hand on cart or cart on hand, it's the same force, because it's only one slap. But think about it, what has more mass, my hand or this cart? Well, probably the cart, right? Does that have anything to do with the fact that the forces are the same? Not at all. So so masses are irrelevant. All I'm saying is there's one slap, there's two ways of looking at it, but the forces are the same. Hand on cart, cart on hand. Same magnitude of force, opposite direction. Okay, let me get something else, which I can't find. What did I do with it? What the heck? Oh, front of my face, golly. All right, so there's a fan. So it's called a fan cart. Okay, a fan cart. Now, come on, I'll go a little faster than that. Okay, so the air is being pushed in this direction, right? Okay, so we can say that the fan pushes the air in that direction. Now, if I let go, what's going to happen? Well, why is that? So the cart pushes the air in this direction, and then the air pushes the cart in that direction, pushes the fan cart in that direction. So the forces are equal and opposite. Okay. So let's pretend that I am in deep outer space and I'm with a big sumo wrestler, and we're standing there at rest, and then we push on each other. Now, what's going to happen? The sumo wrestler is going to move a little bit, and I'm going to go flying, right? But come on, the forces are the same, right? I mean, we just give each other a push. but since I have the smaller mass, I go flying. Why is that? Well, F equals ma, so A equals F over m. Same force, right? I mean, come on. Let's say we go like this. There's only one slap, right? One slap. So the forces are the same, but since I have a smaller mass, I'm going to have the larger acceleration. Okay, now I've got to show you something over here. Okay. Okay, so these have magnets inside, so they're going to repel. Okay, so I'm holding them. They're not touching. I'm holding them so they're not moving. I let go. It's hard to let go exactly the same, right? Okay, so how does the force this one exerts on this one compared to the force this one exerts on this one? What do you think? Well, it's the same, right? I mean, it's the same, Okay, it's the same. Equal and opposite, right? Equal and opposite. Now, let's put a 2 kilogram mass on this one. Okay, the forces are the same, but this one has a smaller mass than this one, so this one accelerates more. Okay, so what are we saying? We said that force is interaction between two or more objects. What we're seeing now is that forces always come in pairs. So here. So, okay. So there's a force, me, on whiteboard. Right? I exerted the force on the whiteboard. But what else happened to me? Look at my hand, it's red. So there's also a force, whiteboard, on me. And the magnitude of these forces are always equal. The directions are opposite. So forces always come in pairs. For this thing, the fan moved the air moved the fan, or cart, whatever you want to call it. So forces always come in pairs. If there's a F, A on B, there's always going to be a F, B on A. And now since I'm putting the vector sign, I've got to put a minus sign, right? So the forces are always equal and opposite. Let's say I jump. I jump, okay? So how come I didn't keep going? Because the Earth is pulling down on me. So there's a force, Earth, on me. But come on, didn't I exert a force on the Earth? Well, of course I did. Remember Newton's law of gravity? Right? That's the gravitational force between me and the Earth. I pull on the Earth pulls on me. But come on, how come, who accelerated more, Earth or me? Obviously me. Why? Because again, A equals F over m, right? My mass is nothing compared to the mass of the Earth. So I have this big acceleration. I slow down, I stop, then I go faster. Right? But hey, I exerted a force on the Earth. I did. All right, so we have the force Earth on me equals minus force me on Earth. Forces always come in pairs. Now, just for fun, I want to show you something. Okay, so again, A equals F over m, right? So what's my acceleration? Well, you better know that, right? My acceleration, what's the force? mg divided by m. So that's just g, right? 9.8 meters per second squared. But let's do the acceleration of the Earth. I mean, come on, I exerted the force on the Earth, right? So therefore, the Earth had to accelerate because I jumped in the air. Well, how much did it accelerate? Well, let's see. So here's the acceleration of the Earth. Okay, so let's just say my force is That's mg, right? So let's just say 700 newtons. Close enough. 700 newtons. But now we've got to put the mass of the Earth. 6 times 10 to the 24th kilograms. Okay? Well, that's approximately equal to 10 to the minus 22 meters per second squared. Now that's pretty small, wouldn't you say? 10 to the minus 22 meters per second squared. So just for fun, with an acceleration of that small, how long would it take to go from 0 meters per second to 1 meter per second? Well, it would take approximately 3 times the age of the universe. Okay? So all I'm saying is the Earth does accelerate. When I jump, the Earth has to accelerate, because I exerted the force on it. But the acceleration is incredibly small. Incredibly small. All right. Let's say we have a little car, all right, collide with a big truck, all right? So, so there's a collision. Agree? There's a collision. Now, how does the force car on truck compare with the force truck on car? Equal and opposite, right? I mean, come on. There's only one smack, right? There's one collision, and they're the same, all right? The forces are the same. But again, are the accelerations the same? Good golly, no. The guy in the car is going to have a very, very large acceleration, which is probably going to kill him, whereas the guy in the truck is going to have a very small acceleration, Okay, so that's the important thing, all right? The force, whenever you have a force A on B, there has to be another force B on A. And now it's going to be equal magnitude, opposite direction. It's as simple as that. That's Newton's third law. Okay. This is, just another example. I already talked about it, but here's Newton's law of gravity between two, let's say, planets, M1 and M2, all right? Newton's law of gravity. So what is the force F1 on 2? What is that force? Well, it's just, Newton's law of gravity, right? Gm1 m2 over r squared. Okay, right? Because, 1 on 2, so 1 is pulling on 2, right? 1 is pulling on 2. Well, what's the force 2 on 1? So now we have 2 pulling on 1. Well, it's the same thing, right? Gm1 m2 over distance squared. So what do you know? I mean, what do you notice? The magnitude 1 on 2 equals magnitude 2 on 1, which is just this, right? I mean, it's easy to see mathematically, right? And so these forces are equal, magnitude, opposite direction. So Randy Knight says that these forces are action-reaction pair. I just say they're a force pair. All right, whatever, okay? Now, if this mass is much, much larger than this mass, are the forces still equal? Well, yeah. I mean, look at the equation, The forces are still equal, but the accelerations will be different. So all Newton's third law, all it says is that the forces are equal, all right? Forces always come in force pairs, and the members of the force pair are always equal and opposite. Okay, so here, this is data, all right? So this is from, our lab, right? So you're going to get to, if we were meeting in person, you get to play with this stuff. But anyway, so here's that aluminum track I just showed you. Here's a cart, two carts that I just used. And this is something that measures force. It's called a force sensor, okay? And these have magnets, right? And so when they come closer, there's going to be a strong magnetic repulsive force, right? Okay, so let's do it. So what we do is we take these carts, and we start them off kind of far away, and we push them close to one another. And again, remember, there's magnetic repulsion, you know? So as they get closer and closer, what happens to the force? It gets small, it gets larger, and then the carts move away, so then the force gets smaller, right? Now, look at this one. Look at the magnitude. Exactly the same, right? Look at the direction, opposite. Okay, now you might not be so impressed with that, because come on, you know, they have the same mass, same speed, you know, whoopee, right? Okay, so now what we want to do, now what we do is we put more mass on this one. Okay, so we have different mass, but now the same speed. Well, look at the data. Same magnitude, opposite direction. Okay, that's pretty cool. That's what Newton's law says. One more time. Now what we're going to do, we're going to keep this one stationary. So this is the light one. This is the heavy one. This is moving. This is stationary. So we move this one towards that one. Measure the forces. What do you notice? Same magnitudes, opposite directions. So I hope you're convinced. All right, so this is for all forces. And it's not just for contact forces, it's for non-contact forces as well, like gravity, right? Gravity is not a contact force, you know. I mean, I'm not, all right? So it's for all forces. I mean, here, this is Newton's third law right there. Newton's third law says forces always come in pairs, and the force that object A exerts on object B is equal to minus the force object B exerts on object A. That's all there is to it, okay? So, but I mean, I think it's a little bit surprising. I mean, let's say we have this big giant truck, you know, moving along. Then we have a mosquito moving along. Well, again, you know, there's only one slap, right? There's only one, you know, right? There's only one when the poor mosquito gets wiped out by the windshield of the truck. So there's only one interaction, right? Bang. But what does Newton's third law says? The forces are the same. Now, which object is going to accelerate the most? Well, the truck's not going to, the truck just keeps going, right? The poor mosquito, you know, right? But the forces are the same. So the force that the truck exerts on the mosquito is the same thing as the force that the mosquito exerts on the truck. Okay, the forces are the same, accelerations are way different. Okay, so here it is, Newton's third law. Every force occurs as one member of an action-reaction pair of forces. In other words, forces always come in pairs, right? If there's a force A on B, there has to be a force B on A. The two members of an action-reaction pair act on two different objects. That's sort of obvious, right? Here, this is the object. Here, this is the object, right? So here you have the two members of a force pair. B is the object, A is the object. Two members of an action-reaction pair act on two different objects. Different. I'm making a big deal about this, right? And you'll see why soon enough. The two members of a force pair are equal in magnitude, opposite in direction. All right, so for the 50 millionth time, if there's a force A on B, there's also a minus force B on A. Okay, that's it. That's all there is to it. Easier said than done. All right, easier said than done. And again, just because the forces are equal, the accelerations may or may not be equal, because the acceleration is force divided by mass. So you have different masses, you can have different accelerations, but we don't care about that now. All we're talking about is the fact that the forces have the same magnitude. All right. Okay. For the 50 millionth time, right? So, okay, yeah, all right? B is the object, A is the object. All right, here we go. So now we're going to probe your understanding. Consider a horse pulling a buggy. Is the following statement true? the weight of the horse and the normal force exerted by the ground on the horse constitute an action-reaction pair that are always equal and opposite according to Newton's third law. So pause your video and figure this out. Okay, what is it? False. Why is it false? The two members of an action-reaction pair act on two different objects. Forces in a force pair never act on the same object. I mean, look. Let's do the question. The weight of the horse. What's that? The weight of the horse is the force earth on horse, right? Okay, what's the normal force? The normal force is the force of the ground on horse. Well, gosh, here's the object here is the horse. The object here is the horse. Remember, you can't have the same object. All right? Forces in a force pair never act on the same object. So, what's the other member of this force pair? So here we have force, earth on horse. What's the other member of the force pair? Horse on earth. What's the other member of this force pair? Horse on ground. Okay, that's all. So this is kind of an interesting question because, you know, I mean, draw the force diagram. You have the weight and you have the normal, right? Now these, you know, these forces are equal and opposite, right? I mean, the horse is not accelerating vertically, I don't think, right? So this force is equal and opposite to this force. I mean, that's true. But just because they're equal and opposite doesn't mean they're members of the same force pair. So that's what you've got to be careful of, okay? If they're members of the same force pair, you can write this. Just because they're equal and opposite, who cares? Doesn't mean that they're members of the same force pair. Okay, a large truck and a small car traveling at equal speeds collide head-on. Regarding the forces, so pause your video and figure it out, please. Okay, well, hopefully, if you understand this, the force truck on car equals force car on truck, right? Equal and opposite, equal and opposite. So there it goes, right? Because again, there's only one collision, right? There's only one smash, you know, one slap, whatever you want to call it. So equal forces. All right, regarding the accelerations in the preceding question. So pause your video and answer this. Okay, we're back. Remember, acceleration is force over mass. So whichever object has a smaller mass has the largest acceleration. So we're going to say that the car, since it has a smaller mass than the truck, will have the larger acceleration. And that agrees with your common sense and your observations, I hope. Okay, one more. When you pull an object, such as a table, across the floor, the forward force by you on the table is equal and opposite to the backward force by the table on you, right? That makes sense. What it says is that the force U on table is equal and opposite to the force table on U. Perfect. Newton's third law. Perfect. Okay. It seems as though these two forces should sort of balance out. So the table can't be moved. But the table does move. Why? So pause your video and figure it out. And I would recommend, when in doubt, draw the force diagram. Okay, so hopefully you figured it out. What's the object? The object is the table. You aren't the object. You're irrelevant, sorry. The table is the object. So if we were going to draw the force diagram, here's the table. All right, now I mean, you know, there's weight, there's normal, there's friction, but the point is there's the force U on table. All right? I don't care about the force table on you. What's that got to do with anything? You aren't the object, right? The object is the table, right? And so this is true here, but the force table on you has nothing to do with the motion of the table, right? This would have to do with the motion of you, which we're not talking about. We're talking about the table, okay? So only one of these forces here acts on the table. This one, right? This one. Okay, so see how they try to trick you with the wording of that one? All right, so just remember that. The two members of a force pair act on two different objects. Forces in a force pair never act on the same object. If you just remember this, I mean, you won't get confused, you know? I mean, you won't. All right, let's quit.